Lecture 2.2, Limits Involving Infinity. This North Dakota sunset is taken in Theodore Roosevelt National Park. Consider the function f of x equals 1 over x. The limit as x approaches infinity of 1 over x equals 0. As the denominator gets larger, the value of the fraction gets smaller. There is a horizontal asymptote if the limit as x goes to infinity of f of x equals a constant, b, or the limit as x goes to negative infinity of f of x equals a constant, which we'll call b. Example. Find the limit as x goes to infinity of x over radical x squared plus 1. The number 1 becomes insignificant as x goes to infinity. It would still have been insignificant if it was 1,000 or 1,000,000. It's still insignificantly small compared to infinity. So we could rewrite the expression, the limit as x goes to infinity of x over radical x squared. However, as x goes to infinity, x is positive, so we could rewrite the expression, the limit as x goes to infinity of x over x, or 1. Therefore, there is a horizontal asymptote at 1. Another example, f of x equals sine x over x. Find the limit as x goes to infinity of sine x over x. This is what the graph looks like. We've looked at the limit as x goes to 0. Now we're looking at the limit as x goes to infinity. When we graph this function, the limit appears to be 0. We know that sine x is between -1 and +1. So for x greater than 0, -1 over x is less than or equal to sine x over x, which is less than or equal to 1 over x. If we take the limit as x goes to infinity of all three terms, we get 0 is less than or equal to the limit as x goes to infinity of sine x over x, which is less than or equal to 0. Therefore, by the sandwich theorem, the limit as x goes to infinity of sine x over x equals 0. Example 3. Find the limit as x goes to infinity of 5x plus sine x all over x. We can split this fraction up, so we have the limit as x goes to infinity of 5x over x plus sine x over x. In the first term, the x's cancel out, and we can separate the two limits. Now the limit as x goes to infinity of 5 is obviously just 5, and we just found the limit as x goes to infinity of sine x over x. So we get 5 plus 0, or 5. Infinite limits. Once again, consider f of x equals 1 over x. As the denominator approaches 0, the value of the fraction gets very large. If the denominator is positive, then the fraction is positive. So we can say the limit as x approaches 0 from the right-hand side of 1 over x equals infinity. And we can watch the function go up towards infinity. If the denominator is negative, then the fraction is negative. And the limit as x goes to 0 from the left-hand side of 1 over x equals negative infinity. we have a vertical asymptote at x equals 0. Example 4. The limit as x goes to 0 from the right-hand side of 1 over x squared equals infinity, and the limit as x goes to 0 from the left-hand side of 1 over x squared equals infinity, because the negative signs would cancel out. The denominator is positive in both cases, so the limit is the same. Therefore, the limit as x goes to 0 of 1 over x squared equals infinity. End behavior models. End behavior models model the behavior of a function as x approaches infinity or negative infinity. The function g is a right-end behavior model for f if and only if the limit as x goes to infinity of f of x over g of x equals 1, and a left-end behavior model for f if and only if the limit as x approaches negative infinity of f of x over g of x equals 1. Example 7. F of x equals x plus e to the negative x. As x approaches infinity, e to the negative x approaches 0. The x term dominates. Therefore, g of x equals x becomes a right-end behavior model. Our test of the model shows the limit as x goes to infinity of x plus e to the x over x is the limit as x goes to infinity of 1 plus e to the x over x, which is 1 plus 0, or 1. Therefore, our model is correct. As x approaches negative infinity, e to the negative x then has a positive exponent, so e to the negative x increases faster than x decreases. Therefore, e to the negative x is dominant. Therefore, h of x equals e to the negative x becomes a left-end behavior model. Once again, we can test it. We take the limit as x goes to negative infinity of x plus e to the negative x over e to the negative x, which is the limit as x goes to negative infinity of x over e to the negative x plus 1, or 0 plus 1. The first term becomes 0 because the negative signs cancel out, and so the denominator is getting very large very fast. So our model is correct. Now let's look at the graphs of these functions. On your calculator, graph f1x equals x, f2x equals e to the negative x, and f3x equals x plus e to the negative x. In our viewing window, we'll graph x from negative 10 to 10, and y from negative 1.43 to positive 11.43. And there are our graphs. Notice that the original function follows the graph of y equals e to the negative x down the left side. That's our left-end behavior model. And as it moves to the right, it follows the graph of y equals x. And that would be our right-end behavior model. Here is another example, and for some mysterious reason, it also seems to be labeled example number 7. F of x equals 2x to the 5th plus x to the 4th minus x squared plus 1 over 3x squared minus 5x plus 7. Right-end behavior models give us 2x to the fifth over 3x squared, because these are the dominant terms in the numerator and the denominator. And this reduces to 2x cubed over 3. So as we move to the right, the graph should approximate the curve of 2x cubed over 3. Often you can just think through limits. The limit as x goes to infinity of sine 1 over x. Well, 1 over x approaches 0, and we know the sine of 0 is 0.